Hey everyone and welcome. In the digital world, we all have that one favorite shortcut for when things go wrong. But what if I told you that math has its own version of that? Well, today we're diving into the ultimate undo button for linear algebra, the matrix inverse.
Think about it. We've all been there, hitting Ctrl-Alt-Z to reverse our last action. It's a lifesaver, right? Well, in mathematics, especially when we're playing around with matrices, we need a tool just like that. We need a way to reverse a matrix transformation, to get us right back to where we started. I mean, look at this. If you've got a simple equation like 5x equals 10, what do? You just divide by 5. Done. Easy. But what happens when you've got a whole system of equations, all bundled up nicely into this matrix form, ax equals b? You can't just divide by a. Division by a matrix, well, it's not a thing. This is the exact problem that pushes us to invent something totally new, something way more powerful. And that powerful new tool is the inverse. Seriously, if you think of a matrix A as a lock that's scrambling up our variable x, then the inverse matrix is the one specific key that unlocks it all. So what is it really? The inverse of a square matrix A, which we write as A with a little -1 superscript, is another matrix that completely, totally cancels out A. When you multiply a matrix by its inverse, doesn't matter which order, you get the matrix version of the number 1, and that's called the identity matrix, I. This right here, this property, this is the whole game. Now, check out how elegantly this one property solves our big problem. We start with ax equals b. Then we take our key A inverse and we multiply both sides from the left. Now on the left side, A inverse and A smash together and become the identity matrix, which is basically like multiplying by 1. And bam, just like that, x is all by itself. The solution is simply the inverse of A times b. Beautiful, right? Okay, so we get what the key does. We understand its power. But how do we actually make one? Let's get our hands dirty and talk about forging an inverse matrix. Good news! For the simplest case, a little 2x2 matrix, there's this fantastic shortcut formula. It's awesome. You just swap the two elements on the main diagonal, you make the other two negative, and then you divide the whole thing by this special number, AD minus BC, which you might know as the determinant. It's fast, it's clean, and trust me, it's one you'll want to remember. But for the big leagues, 3x3s, 4x4s, and beyond, that little formula just won't cut it. We need a more robust, kinda industrial strength process. And that process is called Gauss-Jordan elimination. It's our go-to systematic way to find the inverse for any size square matrix. Now, the setup for this is just brilliant. In its simplicity, here's what you do. You create what's called an augmented matrix. You just stick two matrices side by side. On the left, you put the matrix you want to invert, that's A. And on the right, you put the identity matrix, I, of the exact same size. And now you have one mission, one goal. You're going to use what are called elementary row operations, things like swapping rows or adding a multiple of one row to another. And you're going to use them to methodically, step by step, transform the left side of this thing, matrix A, into the identity matrix. And this is where the magic happens. Seriously. As you're performing all those row operations to turn A into I, the very same operations are happening to the identity matrix that's just sitting there on the right. So the moment your left side becomes a beautiful identity matrix, you look over to the right, and it has automatically transformed into the inverse matrix, A inverse. The key is forged. All right, so now that we have our key, we've got to read the user manual, right? Inverses have some very specific and very important rules that tell us exactly how they behave. Let's look at the top 3. First, if you undo an undo operation, you get right back where you started. So the inverse of the inverse is just the original matrix. Second, and listen up, because this one trips people up all the time, the inverse of a product of matrices is the product of their inverses, but in the reverse order. And third, the inverse of a transpose is just the transpose of the inverse. You can swap those two operations. That second rule, the one about reversing the order, it can seem a little weird at first, but there's a perfect real-world analogy for it. I call it the socks and shoes rule. Think about it. In the morning, you put on your socks, then you put on your shoes. To undo that process at night, you have to reverse the order. You take off your shoes first, and then you take off your socks. It's the exact same logic for matrix inverses. So this brings up a really big question. Does every single square matrix have an inverse? Can every lock be opened? The answer, and this might surprise you, is no. Not every matrix operation can be undone. A matrix that doesn't have an inverse gets a special name. We call it a singular or non-invertible matrix. This happens when the matrix does something that actually loses information. Imagine a matrix that takes a 3D cube and just squashes it flat onto a 2D plane. You've completely lost all the depth information. It's gone forever. There is no way to reverse that and perfectly rebuild the original cube.
So here's a quick little cheat sheet on how to tell them apart. An invertible matrix, well, it has an inverse. After you do row reduction, it has n pivots, a leading one in every row. Its determinant is not 0, and, critically, the only vector it can crush down to 0 is the 0 vector itself. A singular matrix fails all of these tests. No inverse, fewer than n pivots, a determinant of 0, and it can take some real non-zero vectors and completely flatten them to 0.
The legendary Gilbert Strang from MIT puts this most fundamental idea perfectly. He says, an inverse is impossible when AX is 0 and X is non-zero. Just think about that. If your matrix A can take something that exists, a non-zero vector X, and turn it into nothing, the 0 vector, well, how could an inverse possibly exist? There's no matrix in the world that can multiply by that resulting 0 and magically bring back the original non-zero vector. The information is just gone.
So what's the big deal? Why have we spent all this time geeking out over a mathematical undo button? Why is this one of the absolute cornerstones of linear algebra? Because solving systems of linear equations, finding one unique set of answers for tons of variables all at once, is literally everywhere. It's the engine behind our modern world. From calculating the exact lighting and shadows in 3D graphics, to decrypting a secret message by reversing an encryption key, to making sure a complex economic model has one single, stable outcome. The concept of invertibility is what guarantees that a reliable answer even exists.
So yeah, inverting matrices is the key to solving so many clean, perfectly defined problems. But that leaves us with one last, really fascinating question. In the messy real world, our data's noisy and systems often don't have perfect solutions. So what happens when our matrix is singular, or maybe not even square? How do we find the best possible answer when a perfect undo button just doesn't exist? Well, that's a story for another time. Thanks for hanging out with me.